So thanks for giving me the opportunity to speak. Just going to jump in. I'm going to do a linear stability analysis of this somewhat ridiculous setup here. I realize it's super idealized and simple, but this is the result of like a long sequence of idealizations and simplifications until I got to a stage where I can actually understand. So just bear with me. It's a shallow layer of fluid. I'm going to say that the pressure is hydrostatic. I'm going to consider only long waves. It's going to be inviscid, and I'm going to force the velocity profile, which is a function of z, be monotonically increasing, which is typical of channel flows. It also eliminates any possible instabilities in this flow. So we're going to do this simple. What else am I going to do to simplify it? I think that's it. So there's two important scales here: the depth of flow and the surface velocity, which I'm going to use to take measurements. Okay, naively, I would expect that if you disturb this flow at some horizontal location, x0, and at some time t equals 0, you would, I want to quantify what happens to that signal. What does the surface displacement do in time and space? I think you would expect that you get two gravity waves, one propagating upstream, one propagating downstream. And if you make the current really, really strong, then you should be able to send that upstream gravity wave downstream, wash it downstream. There's like a big body of like engineering literature that says that if your fluid number is greater than 1, then you should be able to supercritical case where everything gets washed downstream. So let's see. And my goal, which I'm not going to talk about, is to have a better understanding of hydraulic control in shear flows. So to understand basically the wave or signal propagation. So I'm just going to hit you with my conclusions right away, and then I'll try to convince you that they're true. Maybe I will, maybe I won't. First one is that, well, they're connected. The first one is that normal mode analysis of this situation can give you a completely distorted, even incorrect interpretation of signal propagation, and that a correct interpretation requires something slightly scary sounding called the continuous spectrum that arises at the initial value. Tissues I learned from Jens, thank you, call this continuous spectrum the essential spectrum, right? I'm going to do some pseudo math, and misjudge the audience. I realize now after being here for 3 days that you like the real stuff, but it's too late to change my talk. I already submitted it. So here's the pseudo math. Let's say we've got some linear differential operator acting on the surface displacement, and have some boundary conditions in there too. There's sort of two ways I can see to solve this. There's this sort of classical physical oceanography approach, which is the modal approach. And you look at that differential operator, and even though I haven't written it there because it doesn't exist, you notice that the coefficients are independent of space and time. So you say, I'm going to use the normal mode form, and that's this equation here, right? So you can get these exponential forms for variation in space and time. And then you get this differential equation, which gives you this sort of homogeneous thing. You get the derivatives turned into algebraic operators. And then because I'm assuming long waves, I don't have the wave number in here. And you get this D function, which is very important for this talk. It's called a dispersion function, or I call it the dispersion function. And then if you say there's non-trivial solutions here, then you're going to set this D equal to 0. That's the dispersion relation. And then you're going to solve for the zeros, and those will be the wave propagation speeds, the normal mode phase speeds. There's another way to do this. If you're feeling that this left-hand side is too boring, you can use the initial value problem approach. You can take the Fourier transform and then a Laplace transform. So Fourier transform in space, Laplace transform in time. I'm going to write the Laplace transform variable as C. So usually use S, but in this case, say S is minus I k times C. So C is the Laplace variable. Then when you take a Laplace transform, out pops the initial condition, which has been Fourier transform. You can put it over to the right-hand side. And now if you want to solve this, you divide by the dispersion function. Okay, so it's in the denominator here. And then you invert your Laplace transform by doing a contour integral in the complex C plane. And let me just say, if you have never like inverted a Laplace transform this way, if you just come to the tables, then really you haven't truly lived yet. This is a wonderful experience. You should really try this out sometime. I can give you some nice integrals if you need some. Okay, but the point is, you got to perform this integration. So what you do is you look for singularities, and there's two types of singularities that happen. One is, it clearly comes from these normal modes, right? Where D goes to 0, then you get these pole singularities. That's what people call the discrete spectrum. So they're in discrete locations. In this case, they're all on the real axis because I've eliminated all instabilities. And then what you do when you invert your Laplace transforms, you integrate around these things and you recover your normal modes. Everything's nice. So let's look at a very simple case that I think everybody can understand, even me. And that is if we take the profile to be constant, so just a layered profile, unsheared. I non-dimensionalize everything from now on, I believe, by the surface speed and the depth of flow, so I get a Froude number, right, which is just the ratio of the surface current speed to the long gravity waves, US on GH. Okay. This is what we get. We solve for the zeros. We get two modes. These are interpreted as gravity waves, right? So for small values of F, we've got really strong gravity wave propagation. They go really much faster than current. So they go off upstream and downstream. And then if you make the current really strong, then they asymptote towards 1, which is the dimensionless. So you're washing all the waves downstream. So I think everybody understands this picture also intuitively. So let's look at a more complicated example. My new favorite profile, the exponential profile. So it's going to look like this non-dimensionally. It has a parameter here, a dimensionless parameter, which is basically the thickness of the bottom boundary. So the smaller H star gets, the smaller the boundary layer gets. So I'm going to look at sort of 3 values here. They're all pretty small. So you can make this, actually make H star go to 0. You can basically recover something very close to this layered case that just examined, right? You just have this super thin boundary layer at the bottom. So one might naively expect that you would get similar results, right? So let's make a comparison. So you can solve this all analytically. You can find the dispersion function. I didn't write it there. I'll show you afterwards if you're really curious. This is what we get. So you can see the unshared results of this dash dot and this dotted profile. And then the colored lines, which hope you can see, are what you get for the exponential profile. And I'm using the really small value of H, really thin boundary layer, so it should be a pretty good approximation. And it is, actually, it is. For most of it, so the downstream mode looks really good. And the upstream mode, when it's propagating upstream, looks really good too. Except when the upstream mode is trying to get washed downstream, I mean, it just says, like, no way, I'm not going in there. It makes a hard right turn and sort of asymptotes to stationary wave speed, right? There's something, I find something very disturbing about this. And you see this also in stratified flows with shear as well. You basically do not get any normal modes that would want to go in this region where the profile, the range of phase speeds of the profile. And it's not just the exponential profile. There's this result from the 1950s by Burns, who says, he shows that no modes are possible within the range of U, which in this case is between 0 and 1. No modes are possible. Nobody's going in there. So no wonder it makes a hard right turn. It's not allowed, right? It's off limits, this region. So I find this very, very strange for many years, actually. And I mean, if you think about this physically, what it says is that no matter how strong you make that current, you're never going to wash that wave downstream. Right? It's always going to propagate upstream. I find that deeply disturbing. I think it goes against common sense. Anyway, okay, so my thesis, or my point here in this talk, is that it's not a physical result. This is a mathematical result, and it's because the modal solution is actually efficient, or I don't know what you want to call it, inside this off-limits region, which I started to call the modal gap. I don't know what I should call it, but anyway, this is the range of the velocity profile, and that you need the continuous spectrum to actually fill this gap in physics. There's another type of singularity. There's two types of singularities that you can get in your dispersion function. There's the discrete modes, which are the poles. There's also these things called branch cuts. I'll go in a second into more what a branch cut is, but it's basically a region where this D just jumps discontinuously. It's got sort of step function behavior. And this happens when you've got curved profiles like the exponential profile. It happens along the real axis within the range of a velocity profile. So when you go to invert your Laplace transform, you do your integration in the convex plane, you integrate around these poles and you get a contribution of these poles, but you also get a branch cut contribution. And so you can write the space-time behavior of the surface displacement in terms of this discrete spectrum and this continuous spectrum. Okay? And this is what they look like. Because I'm just interested in long waves, I get no dispersive effects. And I can write the solutions for these normal modes in a very simple way. You've got some amplitude, which can be found from the residues at the poles. And you've got basically a translation of the initial condition by the modal phase speed. But then in the continuous spectrum case, you have something actually which looks very similar. It's just a continuous integral superposition of these things. And the amplitude function is this beta, which is what I'm going to look at in a second. It's an important function which tells you how the amplitude is distributed in phase space. That makes sense.
Yeah, this looks similar to the circle theory, right? What's the relation here?
Semicircle theorem, you mean Howard's semicircle theorem? Yeah, that tells you. That's for unstable modes, is it not? That's for unstable modes, right? That says that the
this condition being smaller than C smaller than X. This is
yeah.
But it has nothing to do with it.
No.
It's not thinking of it.
No, I don't think so. I think a little bit more. I think so.
I guess problem I see is this eta naught continuous mode is not individually solution of original differential equation. Well,
you can get instances where there are no poles, where there are no discrete modes, and there's only a continuous step.
Yeah. And this is 0 and 1, right? Branch cut.
Yeah, in this case it is, but it's wherever the range of the velocity profile is, where there is non-zero curvature.
So I guess you have to go back to this original general formula with phase space integral, and you can show this mathematically. You have that continuous.
Yeah, I did quasi-math, but I did in the paper, I did the real math.
Yeah, oh, you did real
math.
math.
Yeah, I did the real math, yeah.
Yeah, okay.
I think the confusion is why it's 0.
What's it? Oh, sorry. I totally misunderstood. It is 0, I'm sorry, is the initial condition.
That's the initial condition.
Yeah, sorry.
Yeah, okay.
Yeah,
then it's more consistent with what you showed.
Yeah.
With initial approach, initial wave, yeah.
Examples.
I think I got it conceptually.
Propagate this initial condition. The function remains unchanged, there's no dispersion, because the group speed is equal to phase speed, it just propagates. It's a long run. Okay, this beta function looks like it's interesting. So I have an analytical solution for this thing. I'm not showing it here, but essentially you can solve for this beta function in terms of an integral, and this is what you get for the very small H star case, very thin boundary layer. The one which I naively thought should asymptote to the later results, but which doesn't really get. And what you see is that it can be very strongly peaked for certain values of speed. Okay, in this case, I'm comparing this to the unsheared gravity wave speed, which is this dashed line here. So you can see that they're very close together. And so what I did was I looked at the peak, the location of the peak in terms of phase speed of this beta function, and I brought it as a function of a crude number in this plot down here. So this is the same plot I just showed, right, where the normal modes sort of do this hard right turn. We don't want to go into the off-limits bleaching. The downstream mode looks really good. And then this purple curve is the location of the peak of the continuous spectrum distribution. So what you can see is that as soon as the upstream gravity mode decides I'm going to do something really crazy and not get washed downstream anymore, basically the peak of the continuous spectrum says, no problem, taking over. I'll be the gravity wave from now on. And it reflects the actual gravity wave behavior. So let's look at like a real world, simulated real world. I'm going to actually solve the initial value problem now. And we're going to start with the Gaussian hump, the water surface at x equals 0, and then we're just going to let it go and see how it evolves in time. So disturbing it, we're going to see what happens. And what happens is this. You get sort of 3 disturbances. Right? You get the 2 normal modes, and you have a continuous spectrum. The downstream normal mode does its thing. It takes about half of the total surface displacement with it. And sorry, notice that the surface displacement plotted in the colors is on a logarithmic scale. So half the disturbance goes quickly downstream with the normal mode. Basically, the other half is carried by the continuous spectrum, and it moves at what is very close to the unsheared gravity wave speed. And then the upstream sort of weird mode, normal mode carries a super small fraction. I think it's like 1% or so of this initial condition, and it just sort of, stays sort of stationary. So basically what I'm saying here is that the continuous spectrum is not this sort of bizarre thing that you need to satisfy your initial value problem, but it can actually, in certain circumstances, be representative of the gravity, we consider the gravity wave behavior. So it's just as important in this case as the normal mode, and maybe something we should pay attention to. I wanted to go into more why you get this sort of strange behavior of this beta function, why it's so peaked, why it starts approaching normal mode behavior. In order to do this, we need to understand a bit more about the branch cut and something called Riemann surfaces. I don't know if, I bet not all of you spend as much time as I do thinking about Riemann surfaces and branch cuts, so I put this little refresher in. But I think some of you spend more time than I do.
So this is idealization of your program.
This is a pretend dispersion.
Yeah, okay, I didn't read it.
So let's pretend that our dispersion function is the complex logarithm of C. We can write this as the logarithm of the amplitude plus the argument, which is the angle that the C makes to the real axis, is the imaginary part of this function. So this part is actually multi-valued because you can always add a multiple to pi to it, the integer multiple. And so it has multiple values, and you can sort of express this in terms of a sheet or a Riemann sheet where you take, let's say, the complex plane and you sort of give it some more structure, and you write the imaginary part of this dispersion function of the logarithm on the vertical axis, and then on this sheet, the dispersion function will be single value. Okay. Now, normally we just take a cut of this Riemann sheet or a branch of it, and we put a nonsense to this multiple valued business, and we demand, for example, that the argument of C goes between minus pi and pi. And in doing so, that's where we get this cut. Right? So normally we cut the logarithm. Actually, you don't see it in this plot, it's down here below. But you cut it off there, and then when you can't sort of continuously move up along the sheet, you have to drop off. And then the value of this function changes by in this case. our pretend dispersion function. So let's look at the dispersion function, the exponential profile. This is a bit different. This is I think the audience very colorful plot. The colors are the argument of the dispersion function, and the hue or the brightness, which is not important, don't pay attention to it, is the amplitude. You can see where you get this like very rapid change in the colors. You've got a 0, you've got another 0 here close to the branch point, and then you can see across the branch cut, you've got this sort of discontinuous jump in the colors. But what you could do is you could go onto the different branches of the Riemann sheet, and you can look at how this function varies there. That's the sort of interesting activity to do. And if it's getting a little bit abstract for you at the moment, I'm going to try to convince you that this is a geometry you've all seen before. This shopping mall geometry. This is the city center Arnsburg. I know at least some of you in the audience have been to the shopping center. And this is the Rewe. This is where I do my grocery shopping. And this is the ground floor of the center. This is like the principal branch of the shopping center. And if you want to make it single value because there's other floors, then you have to cut it off somewhere. So right here, I'm cutting it off basically in the middle of the escalator, right? So then it's single value, and if you go up the escalator, then you suddenly drop down to the one down there, and that's the branch cut. And but you don't have to do that, right? There's if I want to go to the parking lot, for example, then I have to go around the escalator, and I have to approach from the bottom. So I have to approach from the top, and then I'll go to the basement where the parking garage is. Or if I want to go to the bathroom, I have to go up this escalator. So I have to go up here. So basically, this is like in this geometry, this is the sort of creepy guy giving a picture of the shopping center. So he's standing right here. And then if you go around the branch, that's the Rewe. So that's sort of the geometry that I'm talking about. Hope that makes sense. Okay, so let's take a look at what's on the parking lot level. So that's the standard branch cut that we've been doing so far. We go down to the parking lot and just move this cut. There's no reason why we can't move it. It's just an arbitrary choice to begin with. So let's push it down in a semicircle, and that's what I've done in the bottom plot. When you do that, something kind of interesting pops out. You get this Landau pole. Actually, I don't know what to call it. Some people call it quasi-mode. That can be very close to this real axis. And what's happening in this beta is that as you move h star, the thickness of the boundary layer, closer and closer to 0, you get this more and more peaked and confined beta function, which is acting more and more like a normal mode. And in the limit as the delta function, it is a normal mode. And what's happening is this Landau pole on the sort of other branches is moving closer and closer to the real axis. And that's why you get this sort of normal mode-like behavior. And in the end, you get a gravity wave. Or, I don't know, maybe I should call it quasi-gravity wave. I don't know what the right word for that is. I did quasi-math, and now I got quasi-gravity wave. Okay, these are my conclusions. That's the first two I said already. I think that the normal mode analysis can really give you the wrong idea of what's happening if that's all you do. And that it really requires the continuous spectrum if you want to understand what's happening in the solution, and that the continuous spectrum can represent gravity wave behavior. I mean, or quasi-gravity wave behavior, I don't know. But it basically is where all the physics happens in this modal gap region, and that the amplitude can be large. It can be up to half of the signal. So something maybe you should think about paying attention to. And yeah, for the mathematical details, you can look at this paper. Here's another one of your videos. Thank you.